Hello everyone. Can someone please confirm if you can hear me and you can see me? Oh, great. You can hear me and see me both, right? Mm, okay, great. Let's start the class. So this class is part of four classes, combination of four classes. It is a micro course on game theory in competitive programming. So let's begin. Uh, okay, one moment. Full screen. Okay, so game theory. Who am I? Starting with the basic question of who am I? I am Surya Kiran. Uh, I, I attended ICPC World Finals twice in the past, in 2014 and 15. That's probably the peak of my programming career. That's old actually in 2015. It's already 5 years already, so I am quite old in this arena. So my work experience, I worked in Google London for 1 year and Google Mountain View for 3 years. And then I have quit my job to work on my own startup, and I am trying to build my own startup right now. So I did my bachelor's from IIT Roorkee. So there's that. Uh, and my teaching experience, I have taught weekly lectures to my juniors, and I have attended some programming camps, and I have also taught like 4 Unacademy classes so far. So this is my fifth. And the bigger question of what are we doing and what's the whole thing like about the whole course, like what you guys will be learning, that's here. So please take note of this if you can. Like in the beginning, in the first class, we'll be dealing with basics and some puzzles uh, to develop understanding of like what exactly is game theory, like how will it be uh, in the competitive programming, like how to develop that attitude kind of things. And in the second class, we are going to learn about the minimax algorithm and a special game called NIM. This is probably the most famous mathematical game ever. So we are going to discuss this game as well, NIM. And in the third class, we are going to talk about numbers, like to assign some number to each sub game, like multiple games were there, like complex games. There is the Sprague-Grundy theorem that we are going to learn in the third class. Uh, so uh, the name looks complex, but it's very simple. And in the fourth class, we are going to solve a bunch of competitive programming problems. Like we'll try to apply all the understanding that we had in the first three classes into the fourth class. So there's that. So let's start today's class. Okay. So before starting the today's class, like there is something important to announce. Like there is something called CodeChef laddus. Like if you guys know, like if you have used CodeChef before, so there is something called CodeChef laddus. You can use laddus to get some gifts or presents. So let's start by playing a game. Okay, like we are going to start this game class uh, like without any understanding of the class. Like let's try to play a game, and free laddus if you win. If you win, like you can earn some CodeChef laddus. So I'll paste a form in your chat. So open this form and either pick 20 laddus or 10 laddus. Only the first 100 responses in the next 5 minutes will be considered. And if more than half of you pick 20 laddus each, no one gets any laddus. Only the first 100 responses to be considered in the next 5 minutes. Open that form that I pasted in the chat. You need to sign in, Akash. I believe the link is working. Yes, the link is working. So let me paste the same link in. So the ones using YouTube, I pasted in the YouTube chat as well. So can anyone open the link? Like, can someone in Unacademy please reply if you can open the link? Okay, Saurabh can open, Akash. I'm not sure why you can't open. Okay, so the game is simple. It's very simple. Like, you just open that link and pick how many laddus you want. You don't copy, Akash. Like, just click on the link which is there in the chat. There is a link in the chat. I pasted a link in the chat. You just click on that link. You will be redirected to that form. So just pick how many laddus you want, either 20 or 10. If you want to be greedy and pick 20, if more than half of you pick 20, then no one gets any laddus. If you want to be a little less greedy and you pick 10 laddus, and if more than half of people pick 10 laddus, then everybody gets the laddus that they picked. Okay, yes, I pinned the link, Adarsh. So, in YouTube, Bhaskar, the link is present. I pasted a link in the chat, and there is also a link in the video, so you can pick either of them. Ayush, please see the link with my name, like Surya Kiran. I posted it from my personal account, Surya Kiran. So just open that link and select either 20 or 10. If more than half of you select 20, nobody gets any laddus. If you still have 2 minutes left, uh, okay. Before 7:10, whoever opens, whoever you also need to enter your CodeChef ID so that we can give you laddus to that ID. Don't forget to mention your CodeChef ID. Okay, so I am ending today's contest, like the game. Uh, the time is over. 5 minutes are over. Uh, you can't pick any more laddus. So there have been around 26 responses, and okay, I want to give 2 more minutes, like uh, till 7:12. I'll see, like 2 more minutes, 7:12 p.m. IST. Before this, try to submit your uh, option. If you select more than, if more than 50% of the people select 20, then nobody gets any laddus. So please don't try to be greedy. Try to optimize your scores. Like if many people are greedy, then nobody gets any laddus. Ayush, the laddus are not normal laddus. They are CodeChef laddus. They'll be added to your CodeChef account. I just posted the link with my name, Surya Kiran. Okay, time is over. Let's look at the results. It's 7:12. Okay, the results are there have been 30 responses, and unfortunately 53% of you guys have selected 20 laddus. So the time's up. No laddus for anyone. So everybody was greedy, like 53% of the people were greedy. So sorry guys, no laddus. No, this is not fake, Ankit. uh, Genuinely I wanted to give you guys laddus. Like I can share the summary responses as well. Like this is not fake. Okay. Okay. I'll share by the end of the class if you want. So 53% of the people selected 20 laddus, so nobody is getting any laddus. So what did we learn today? Like in this game, what have you learned? You learned how to think about other people. So it's not just you selecting your number of laddus, you also need to think about what other people will select. So there are like, it's not very straightforward. This is like two levels. So that way we are going to see how complex games can be solved. Okay. So let's go to the next game. So games. So today we are going to discuss about games. What kind of games? We are not going to discuss about these kind of games. We are going to discuss more about these kind of games. Like there are some coins on the board, and A takes 2, B takes 3, A takes 1, like that kind of games. The game that we just played before, like 20 laddus and 10 laddus, something like that, we are going to uh, play. Okay. And so today we are going to learn about 1 or 2 person games. We are not going to learn about like multiplayer games or anything. And all the games that we are going to learn today are perfect information games. Like in some card games, like you don't know what other people's cards are. But today's game, we are going to learn about perfect information games. No chance moves. Like there are no chance moves. Like there is no random thing that you will do, like throwing a dice or random number generator as such. There will be no randomness in the game, and there is always a win or lose or draw outcome. Like it's not like the game is abandoned in between. Like there is always a win or lose or draw. Like every time the game will end. So a question for you guys. I want to create a poll. Uh, does poker fall in the above criteria? Okay, this is a bit depressing. 50 around 45% of the people selected yes. No, poker does not fall under above criteria. In poker, in the beginning, like randomly we give cards to each other, right? So there is no chance moves. This point fails. Like in poker, there are chance moves. There is probability, there is chance, and everything, right? And it's also not a perfect information game. Like in poker, you don't know what the other player is holding their cards, right? So poker does not fall under that criteria. And does chess fall under that criteria? Let's see a poll. Mm, okay, 75% of the people gave the right answer. So it's a two-person game, chess. The first point is true. Perfect information, like yes, everybody knows what the other player will play, like all the pieces where they are, you know. And no chance moves, like you're not throwing a dice or you're not throwing any random number generator. So this satisfies. Win or lose or draw. Every time you play chess, there is always a win or lose or draw outcome. So, yes, poker falls under this criteria. Another question. Does Monopoly fall under this criteria? Okay, good. 72% of the people gave the right answer. Because Monopoly, you throw dice, it's not 10 coins. Like on a table, there is a table, there are n coins on it, and a player can make any number of turns, and in each turn a player can take either 4 coins or 7 coins. Either 4 coins or 7 coins. A player wins if they can take all coins. Okay, so let's say initially there are 11 coins on the board. Can you win? There are 11 coins on the board. You can take either 4 coins or 7 coins. Can you win? Let's take a poll. Okay, around two-thirds of you gave the right answer. Uh, yes, you can win. First, you can take 4 coins away and then take 7 coins away. Total, you're taking 11 coins. You take all the coins and you win. If you have 13 coins on the board, can you win? Okay, great. 85% of you selected correct answer. No, you cannot win if you select 13 coins. Because whatever combination of moves you play by taking 4 or 7, you cannot take all the coins. Okay, so another question. Does this game satisfy all of these criteria? All of these criteria, does this game satisfy? Okay, around two-thirds of you gave the right answer. I don't know why you guys selected wrong answer. Is it a one player or two-person game? Yes, it's only one person game. We already told it. Is it a perfect information game? Yes, you always know the number of coins on the board and you always know which moves you can make. So it is perfect information. Are there any chance moves? Are you rolling any dice or are you taking any chance or risk or anything? No, there are no chance moves. And there is always a win or draw or lose outcome. Yes, after the end of your turn, after end turns, you can always tell if you won or lost. If there are no coins on the table, you win or else you lost. So yes, this satisfies all the conditions. So there was a question of explain no chance move again. Chance moves are those where there is a random number or there is randomness in the game. Like for example, in some games we throw dice, right? So throwing a dice is like chance. Like you don't know which number rolls. Like let's say Ludo or Snake and Ladders. You do roll a dice, and whatever number comes, those many steps you move forward. It is always a chance, right? You don't know how many you will. But in a game of chess, you always know which move you are gonna make. You're not gonna roll a dice or do any random thing. You calculate and make a move. That's called no chance moves. So so here we have to understand a small concept of states and moves. To understand this game better, like you need to understand what states and moves are. Like a state is something that describes the current situation of the game. Like initially there are n coins. So how do you describe? So state is all that information that describes the current situation. So what can be the state here? The state can simply be n coins. We can also store information whether it is a winning position or losing position. Okay. So if there are n coins, we can store whether this is a winning position or a losing position, right? Okay. So this can comprise the state. Is it clear? Uh, so what are moves? Like initially there are n coins. This is our state. We can move to state of n minus 4 or we can move to state of n minus 7, right? We can either take 4 coins or we can take 7 coins. So either you move to state of n minus 4 and you move to state of n minus 7. And we also store winning position or losing position, right? So either if n minus 4 or n minus 7, if one of these is winning position, then n is also winning position. If this is a and this is b, the position of this, the position of this will be c equals to a or b. Or is the logical or of the two boolean values. If we store n minus 4 comma a, n minus 7 comma b, the situation here n comma c will be c equal to a logical or b. Okay. If one of these is winning state, then n is winning state. Okay, is this clear? The concept, basically the moves are like you are in current state, all the states that you can reach are the moves, like you can make those moves. Okay, so there is that. Now let's look at a different question now. Okay, at the beginning there are 9 coins. Okay, in the beginning on the table there are 9 coins, and two players are playing a game. It's a two-player game, and they alternate making turns. Like in the previous game, we saw that there is only one player, but in this game there are two players. First, the first player. Let's say there are two players A comma B. First, A plays a move, then B plays a move, then A plays a move, and B plays a move. Like alternatively, they take turns to make a move, like that. Let's say A is Alice and B is Bob. First Alice moves, then Bob moves, then Alice moves, like that. And when it's a player's turn, they can take away 2 to the power of k coins. Like 2 to the power k can be any whole number. It's either 2 power 0 1 coin, or 2 power 1 2 coins, 2 power 2 4 coins, so on, 2 power k coins. Like you can select any number of coins uh, which are the power of 2. There are two people playing a game, Alice and Bob. First Alice starts. So whoever takes away the last coin is declared the winner. It doesn't matter how many coins you have in with you. Whoever takes the last coin is declared winner. Does the first player win? Okay, around roughly half of you have selected the right answer and half of you have selected the wrong answer. The answer here is yes, the first player wins. Why? Let's see. Let's say there are only 3 coins, or let's say there is only one coin on the table. Who will win? The first player. They can directly take away the first coin. So, first player wins. If there are 2 coins, who will win? The first player can take away both the coins. So, first player wins. They'll take away 2 power 0 coins, they'll take away 2 power 1 coins. If there are 3 coins, what are the moves that first player can take? They can either take 2 power 0 that is equal to 1 coin, or 2 power 1 that is equal to 2 coins. So if they take 2 coins, if they take 1 coin, they will give this state to the second player, right? So initially you are in state with 3 coins, you take away 1 coin, you go to state of 2. You take away 2 coins, you go to state of 1. This in this state first player wins. In this state first player wins. So in this state the first player loses. Like if Alice is having 3 coins, then she can give either 2 coins state to Bob or 1 coin state to Bob. If she gives 2 coins state to Bob, Bob will take away 2 coins and he wins. If she gives 1 coin state to Bob, Bob will take 1 coin and he wins. So Alice can only lose here. So here second player wins. 4. You can either take 1 or 2 or 4. You can take away all the 4 coins, the first player, so first player wins. 5. You can only go to 4 by taking 1 coin, or 3, or 1. By taking away 2 coins, you can go to the state of 3. If Alice is playing first, she can give the state of 3 to Bob. Bob will be first player with a state of 3. Alice is the first player with a state of 5. So she gives state of 3 to Bob, which is losing for first player. So in this state, Alice wins. So in this state, Alice wins. She can move to a state where she can win. So that's why 5 comma A is Alice win, first player win. 6, you can either move to 5 or 4 or 2. 5, 4, 2. All of these the first player wins. So here you cannot move to place where second player wins. So this is second player wins. Like from 6 you can only go to 5 or 4 or 2. All of these 3 states are winning for the first player. Like if Alice is first player of 6, Bob is the second player. In 5, Alice will be the second player, Bob will be the first player. In 4, Alice will be the second player, Bob will be the first player. In 2, Alice will be the second player, Bob will be the first player. In all of these states, the first player wins, so Bob wins. So she cannot move to any state where she wins. So this one, Bob wins. This is the winning state for Bob. So second player wins. 7, you can do the same analysis and prove that for 9, second player wins. Okay, I hope you guys understood this. Did you guys understand? Just creating a poll. Just want to see how many of you understood this, because this is very important. Okay, around 70% of the people understands this. Okay, fine. Let's move on to the next question. So before moving on to the next question, let's write a pseudocode of this. Like the position is the state that we have, the number of coins on the board. We are writing a function which returns whether this is winning or losing for the first player. So moves are all the possible positions that you can go. If for all x in moves, if all of them are winning, then we return false. If one of them is losing, then we return true. Okay, so that way we try to see if there is a state or position, we can move to 3 positions. If one of these 3 positions is a losing position, this is a winning position. If all of them are winning positions, this is a losing position. Okay, so there is that. So let's try the same problem, but this time we have 10 to the power of 9 coins, like 100 crore coins. Okay, the first player is it winning for them or losing for them? I'll give you 30 seconds for this. Okay, around 2/3 of you gave wrong answer. The answer here is false. Like if we take the previous slide, there is a simple pattern here. Like 3 is winning for second player, 6 is winning for second player, 9 is winning for second player. Like this, if there are n coins, if you divide n with 3, if it is equal to 0, then it is losing for first player. Else, it is winning for first player. Why is this? If n mod 3 is 0, the simple case we can verify this is by looking at 0. If there are 0 coins, then it is losing for the first player, right? Like if there are 0 coins on the table and it's your turn to make a move, then it means that in the previous turn, the second player has taken the last coin away. So the second player is winning if there are 0 coins on the table. If there are 0 coins, then the second player is winning. If there are n mod 3 equal to 0 coins and n greater than 0, then whatever number of coins you take, like you take 2 power k coins, whatever number of coins you take, you will always go to a state for which the remainder when you divide with 3 is not equal to 0, because 2 to the power of k is always not divisible by 3. You take any k, 2 power 0 is 1, 2 power 1 is 2, 2 power 2 is 4. Like any 2 power you take, the remainder is not equal to 0. So if you take 2 power k coins away from the state, like if you are in n mod 3 equal to 0 state, you will always move to a state where n mod 3 is greater than 0. This is because you are taking away 2 power k coins. This mod 3 is not equal to 0. So if you are subtracting that number of coins from n, the n mod 3, the new n mod 3 will be always greater than 0. So that's why you can only move from this. And from n mod 3 greater than 0, you can always move back to n mod 3 equal to 0. If n mod 3 was 1, you take away 1 coin. If n mod 3 was 2, you take away 2 coins. You can always move it back to n mod 3 equal to 0. So that's why if n mod 3 equal to 0 for n equal to 0 was losing, so n mod 3 will always be losing, because it can only go to n mod 3 greater than 0. And from this winning position, you can always go to a losing position. So that's why this is a winning position. I repeat, like using mathematical induction, for n equal to 0, if n mod 3 was losing, because there are no coins and the second player has already won because he did the last turn. So n mod 3 greater than 0, it is, let's assume it is winning for some n. Now for n greater than n, now some m, for m greater than n, if it mod 3, if it's greater than 0, let's say m equal to n plus 1. If m, if its mod is greater than 0, then we can always go to equal to 0 by picking 1 or 2 coins. So you can always push back the person to the losing state. That's why. Any questions so far? Like, do you have any questions? Please. The first 10 power 9 is not divisible by 3. That's why second player wins. If it was... Oh, sorry. I made a mistake. Yes, the first player wins here. The right answer is yes, the first player wins. 10 power 9 mod 3 was greater than 0. So that's why the first player wins. Okay, because he can always move to 10 mod 3 equal to 0 state. Like let's assume that till 9 10 mod like n mod 3 equal to 0 or not equal to 0 holds. Okay, now using mathematical induction, like let's say 10. So from 10 you can always move to a losing state. Like you can take either one coin or two coins. You can always move to n mod 3 equal to 0 state. Okay, till n, if it is true, n plus 1 will also be true, because from n plus 1 you can either take one coin or two coins if its mod is greater than 0 and go to n minus 1 or n minus 2 and go to a losing. If you're going to a losing state, then this is a winning state. Okay, example with a small number, like you can just go to the previous example, like for 9 number of coins. From 9 you can either go to 8 or 6 or 5 or 1. Like you can either take one coin and go to 8, two coins and go to 6, three coins and go to, sorry, four coins and go to 5, and 8 coins and go to 1. And oh, sorry. One coin and go to 8, two coins and go to 7, four coins and go to 5, 8 coins and go to 1. So all of these states are first player winning states. 8, 7, 5 and 1, all of these are first player winning states. So that's why this is a second player winning state. Okay, so if there is n mod 3 greater than 0, you can always go to n mod 3 equal to 0. Okay, I would suggest you think about it for a while. After the class you will get a better idea. So let's go to a different puzzle right now. So let's say there are 6 cards on the table. Like there are 6 cards. There is a table. There are 6 cards. And you and I are playing a game. You as in the student and I am playing a game. We both are playing a game. Okay. And each card has one number written on it, and we don't know which card has one, which card has two. Like each card has a distinct number as well. No two cards have same number, and all cards are lying face down. So both of us don't know which card is which. You and I pick a card randomly. Okay, you and I pick a card randomly. The player who has the higher number card at the end of the game wins. Okay, and you don't know what I have, and I don't know what you have. You and I pick one card from 6 cards. Like I pick one card, you pick one card. You don't know what I have, I don't know what you have, and your card has number 2 written on it. Okay, I offer you a trade. Like I say, let's swap cards. Like I'll give you my card, you give me my card, and whoever has the higher number wins. Okay, and your card has number 2 written on it. Should you accept my trade? Like, is it better for you to accept my trade? I'll give you 2 minutes to think on this. If anybody want me to repeat the question, I'll repeat the question. There are 6 cards. Each card has number 1 to 6 written on it. All cards are lying face down. You don't know which card has which. The player who has the higher number card wins. You pick one card, I pick one card. You know that your card has number 2 written on it. You don't know what my card has. It can either be 1 or 3 or 4 or 5 or 6. Okay, so there is a higher chance that it will be more than 2. Okay, because we randomly picked a card. And I offer you to trade the cards. Okay, Normally I don't, but today I felt like I should offer you to trade our cards. Would you accept my trade and take my card and give me your card? Just drink some water. Okay, so not so surprisingly, most of you gave the wrong answer. This is not a simple problem, okay? Like, why did I offer you to trade the cards? That's because I know that I will be getting a better card. Okay, let's try to see working from backwards. Okay, if this is winning or losing, around like 72% of the people gave wrong answer. Let's see why. um, because in the beginning it might mean like it is a really good offer because like I can have 3 or 4 or 5 or 6. There is very less chance of me having a 1. So like in 4 out of 5 cases you will be getting a better card. But would I have given an offer if I was having either one of these 6? Like if I am having the card number 6, I will definitely never offer the trade, right? Because it is the best card. I will not offer you the card number 6. If I am having card number 5, I know that if you have card number 6, you will never give me card number 6. So offering you card number 5 will always be bad for me, because if you accept a trade when I offer you with card number 5, that means that you have either 1 or 2 or 3 or 4. Like if I have 5 and you can have 6 or 4, 3, 2, 1. Okay, I am having 5 and I offered you a trade. If you have 6, you will definitely not accept. If you have one of this, if you accept, it is losing for me. So offering you is bad for me. If I have 5, I will not offer. Because if I offer, if you have 6, you will definitely not accept. And if you have one of these, if you accept, it is bad. If you don't accept, it is good. But if I have 5 and if I offer, it is always bad. That's why. Like in the same way, if I have 4, let me add a slide. Okay. Uh, let's say I have 4. You can have 6 or 5 or 3 or 2 or 1. Okay. This is mine. This is yours. Okay. If I have 4, if you have 6, you are definitely not trading. If you have 5, you know that I will not trade with 6 or 5. You know that definitely I have some card less than 6 or 5. So that's why you will not give 5. You will not trade with 5. If you have 3 or 2 or 1, if you accept my trade, it will be bad for me. So I know that you will not accept the trade if you have 6 or 5, and all the cases where you accept are bad for me. So that's why I will not offer with 4 as well. In the same way, I will not offer with 3 as well. I will offer you a trade only when I have 1. So you should not accept my trade in any case. Like whatever you are having, the card you are having, you should keep it. Did you guys understand this? I'll just create a small poll. Uh, did you guys understand this? Okay, around half of you understand this. Uh, I'll skip this then. Uh, you can go back to the previous past few minutes and revisit that thing. Uh, just taking a question. Explain the case with three cards. Let's say there are three cards, one, two, or three. Okay, and you pick a card randomly, and I pick a card randomly. And your card is two, and my card it can be either one or three. Your card is two, my card is either three or one. Now I am offering you a trade. Like, would you swap my card? Will you swap it or not? You should not swap the card, right? Because if I have the card number 3, I know that I have the highest number of card. I will not offer you the trade because I am already winning, right? So I will offer you the trade only when I have the card number 1. So that way you know that I have the card number 1 when I offered you the trade, and you will not accept that card. If you if you extrapolate this to 6 number of cards, you will know that you should never accept my trade. Okay, let's go to the next one. So I'll give you like 2 minutes to read through this. I know this is like a big statement, but please bear with me and read this. It is a very famous uh, thing. Like, it's called prisoner's dilemma. So uh, it is a very important theorem in game theory. Okay, here it goes. Like, there are two members uh, who are imprisoned. They are arrested by the police and they are imprisoned. Each prisoner is in a solitary confinement. That means that there are two prisoners, A and B. Uh, A doesn't know what B is saying or doing. B doesn't know what is A is saying or doing. So that way, they both are in solitary, like they are in like complete solitude. They can't communicate with each other. So the prosecutors lack sufficient evidence. They don't know if the crime was committed by these two or not. But they have enough to convict both on a lesser charge. Uh, so the police say that, like, they will go to each of the prisoner A and B. They say that if you betray, like if you betray and like say that you committed the crime and your opponent doesn't betray, then you will be going free. Like, I'll give you a free pass. Like, I go to A, I'll tell that if you confess, I will give you a free pass and uh, jail B for 2 years. Okay, if sorry, jail B, not 2 years, 3 years. If you confess and B doesn't confess, then I'll set you free and B will serve 3 years. If both of you confess, both of you will get 2 years. If you remain silent and B confesses, then you will serve 3 years and B will be set free. If both remain silent, both of them will be set free. Okay, so the question is, like, if you are one of the prisoners, will you confess or not? Like, what is better for you? Like, you are, let's say you are A, will you confess or not? Okay, 50% of the people said the right answer. Yes, you should always confess. The reason is this, like, let's like take a look at the payoff matrix. Like, if B remains silent and A stays silent, both of them will receive 1 year each, right? And if B betrays, A remains silent, B receives 0, A receives 3. If A betrays and B remains silent, B gets 3, A gets 0. A betrays and B betrays, both of them get 2 each, right? So you are A. In this case, you either get 0 or you get 2. So the average, like the expected outcome of your prison time will be 0 plus 2 by 2. Okay, that is equals to 1 year. If you stay silent, you will get either 1 year or 3 years. The average of that is 1 plus 3 by 2, that is equal to 2 years. So the worst case scenario is bad, and the average case scenario is also bad when you remain silent. So you choose to betray. So this is actually a very interesting problem because there are so many problems related to this kind of problem where, as a group, if they help each other, it is better for everyone. Like, if both of them remain silent, both of them get 1 year each. But they choose to betray each other and still get 1 year each. Like, sorry, they choose to betray each other and get 2 years each. Okay, because they want to reduce the expected outcome. So a rational being will always try to betray the other person, like, because the expected outcome is lesser for when you betray, right? This is a paradox. Like, if you cooperate with each other, you both get one, but you choose to not cooperate by betraying because the expected value is lesser. So, okay, expected outcome. So, like, in every box there is this diagonal, sort of. The lower one is the number of jail time for A, upper one is for B. Okay, you are A. Okay, and you, if you if you stay silent, you either get 1 year or you get 3 years, right? So you either get 1 year or 3 years. Like, if you think that the other person rolls a dice, you either get 1 year or 3 years. So the expected is 2 years, right? So if you betray, you either get 0 years or you get 2 years. The expected is 1 year, right? So you choose to betray because the expected is less. Uh, there are other explanations as well why you always choose to betray. We can discuss that in the future classes. So based on this, you choose to betray. So we don't have time to take questions now. Please attend the next class if you have any questions. Uh, and these are some resources for you for the next class. Like, we'll be discussing about the game of NIM, and we'll also be discussing the game of Minimax. Sorry, an algorithm called Minimax to solve many game theory problems. So unfortunately, you guys could not win laddus today because 53% selected 20 laddus. Sorry for that. Uh, Thanks, guys. Okay. Thanks for your presence. If you have any questions, please come to the next class. I'll answer there. Thank you very much.